So welcome to the talk on a complete characterization of infinitely repeated two-player games having computable strategies with no computable best response under limit of means payoff. The name of the paper is very long because first, all of the short and cool names were already taken 25 years ago. But second, it describes almost perfectly what the paper is about. So now you can skip watching the talk, unless you want to know how surprising the characterization is or how we obtained it using some standard techniques in a smart way. In the next few slides, I will just very briefly explain what all the terms used in the paper, in the name of the paper, mean. By a game, we mean a normal form game, which is defined by n, the set of players represented by numbers 1 to n, a, the set of action profiles, where each player has a finite set of actions available, and ui, the payoff function for each player I. We consider only two-player games that are represented by a payoff matrix with player 1 as a row player and player 2 as a column player. Standard examples of games are rock, paper, scissors and prisoner's dilemma. And here you can see the payoff matrices of these two games. Given a game G, we denote G infinity a game that consists of infinitely many repetitions or stages of the same game G. A finite history of length t is a sequence of t action profiles played in the first t stages. We say we call a player I strategy a map that outputs the next action played by all previous stages played by all players. A strategy profile is a tuple of all player strategies, and it induces a unique path of play, which is an infinite sequence of action profiles. There are more ways to define a payoff in an infinitely repeated game from the infinite sequence of payoffs. We use only the limit of means payoff, which is the limit inferior of the average stage game payoff. To illustrate these definitions, consider the game rock, paper, scissors from the earlier slide, and consider these simple strategies. Player 1 always plays rock, and player 2 plays rock in odd stages and paper in even stages. Then in the odd stages, the action profile played is rock, rock, and in the even stages, the action profile played is rock, paper. The payoffs of player 1 alternate between 0, a tie, and -1, a loss. So player 1 earns the limit of means payoff minus 0.5. Player 2 earns 1 in even stages instead, hence his limit of means payoff is plus 0.5. Next, we define relationships between strategies. We say that a strategy is a best response to the opponent's strategy if there is no other strategy that earns a higher payoff. We say that a strategy profile S is a Nash equilibrium if it consists of strategies that are best responses to each other. In a Nash equilibrium, no player has an incentive to deviate from their strategy in order to maximize their payoff. A Nash equilibrium is subgame perfect if it is a Nash equilibrium in the infinitely repeated game following any possible finite history. This way we ensure that the strategies forming an equilibrium involve only credible threats. And the last missing piece is the definition of a computable strategy. We say that a strategy Si is computable if there is a Turing machine that computes it, that is, on any binary input representing a finite history H, halts with the binary output representing the next action played by player I. In 1994, Knobloch showed that infinitely repeated prisoner's dilemma admits a computable strategy that has a best response, but no such best response is computable. 2 years later, Nachbar and Zane proved that when the payoff is computed as a discounted sum, any game that has the prisoner's dilemma in a way embedded in it also has a computable strategy with no computable best response. And they also strengthen the requirement of having a best response to forming a subgame perfect equilibrium instead. These two classic results provide necessary conditions for the existence of games with a computable strategy that has no computable best response. Our goal is to find a characterization of the class of two-player normal form games, and we denote it CBR, such that there is a strategy profile S of the infinitely repeated game, satisfying that S1 is a best response to S2, S2 is computable, and S2 has no computable best response. Similarly, we define a class of games C and E, where we require S to be a Nash equilibrium. So instead of just S1 being a best response to S2, S2 is also a best response to S1. And last, the class CSP requires S to be a subgame perfect equilibrium. Notice that CSP is a subset of the class C and E, which is a subset of the class CBR. Now, when we have our problem defined in detail, let us start with our results for the first class, CBR. We say that the game G is trivial for player I if the maximum stage payoff of player I, so it's this value, equals his min-max value, which is the minimum value that his opponent can force him to earn. For example, rock, paper, scissors is trivial for both players, while prisoner's dilemma is non-trivial for both players. Notice that if G is trivial for player 1, no matter which action player 2 plays, player 1 can always obtain the maximum stage payoff, as long as he knows what player 2 is going to play in each stage. This leads to the following observation. If G is trivial for player 1, then every computable strategy of S2 of player 2 has a computable best response, which in each stage computes the next move of player 2 and plays the action maximizing the payoff in the current stage. Surprisingly, and this is our first big result, non-triviality is necessary, but also a sufficient condition. That is, G is non-trivial for player 1, if and only if G belongs to CBR. That is, player 2 has a computable strategy that has a best response, but no computable best response. As a side result, parallel to Knobloch's paper, G being non-trivial is also equivalent to the existence of a strategy that has no best response and to the existence of a computable strategy that has no best response. However, we skip the proof of this theorem here. Our second result says that the classes C and E and CSP are equal. And again, G belongs to the class C and E, or CSP, if and only if player 1 has at least 2 available actions. And there is a Nash equilibrium S prime of the infinitely repeated game, where player 1 earns the limit of means payoff that is strictly higher than their min-max payoff. We will see shortly that this condition is satisfied by almost all games that admit a Nash equilibrium, which means that the classes C and E and CSP are very rich and contain games that are very different from Prisoner's Dilemma. Because any subgame perfect equilibrium is also a Nash equilibrium, condition B apparently implies the condition A. First, we will prove that the condition A implies condition C. But the proof relies on the Volk Theorem, which is a standard result describing the set of payoff profiles that are achievable under a Nash or subgame perfect equilibrium of the infinitely repeated game. We say that a payoff profile is individually rational if all players earn at least their min-max payoff, that is, at least the minimum payoff the other player can force them to earn. Second, a payoff profile is feasible if it is almost a convex combination of the stage payoff profiles, but we require the coefficients to be rational for computability reasons. The Volk theorem intuitively says that the set of payoff profiles achievable under an equilibrium, whether it is Nash or subgame perfect, is equal to the set of feasible and individually rational payoff profiles. However, we will use this slightly different form of the Volk theorem, again for computability reasons. Moreover, and this is important, proof of the Volk theorem is constructive, and the strategies involved in the equilibria are computable. We prove the first part by showing that the negation of the condition C implies the negation of condition A. That is, we want to show that if player 1 has only one available strategy, or every Nash equilibrium gives player 1 at most his min-max payoff, then every computable strategy of player 2 forming a Nash equilibrium has a computable best response. That is, the game does not belong to the class C and E. Having only one action implies that player 1 has only one available strategy, which is clearly computable. Now, let S be any Nash equilibrium of the infinitely repeated game. By our assumption in the Volk theorem, player 1 earns exactly his min-max payoff. Now we use the same trick as before. In each stage, S1 bar computes the next action of player 2 and plays the action maximizing player 1's payoff in the current stage, which is always at least his min-max payoff. But because S1 is the best response to S2 and S1 bar earns as much as S1, S1 bar is also the best response to S2 and is clearly computable. The main idea of the proof of the second part, that the condition C implies the condition B, is as follows. The Volk theorem gives us an equilibrium consisting of computable strategies with the same payoff profile as S prime. We modify the equilibrium such that in some stages, player 2 incorporates a test where player 1, in order to respond optimally, has to solve a problem that cannot be solved by a Turing machine. Incorrect choice of an action by player 1 will be later discovered and punished by player 2. Before we define the undecidable problem, consider the standard Gödel numbering of Turing machines and let Tm of n be the output of the mth Turing machine on the input n. We say that the set A is recursively enumerable if there is a Turing machine that halts exactly on the elements of A. And a set is decidable if there is a Turing machine that halts on all inputs and accepts exactly the elements of A. And last, we say that two sets are recursively inseparable if they are non-overlapping and there is no decidable set C that separates them. That is, A is a subset of C and B is a subset of the complement of C. Now consider the following two sets, A and B, where A consists of all inputs n such that the nth Turing machine halts on n and outputs 0, and B is the same but with non-zero output. Similarly to the famous halting problem, sets A and B are recursively enumerable but undecidable. And what is the most important, and A and B are recursively inseparable, and we will use these sets to force player 1 to separate them in order to respond optimally. Returning back to the proof, given that there is a Nash equilibrium where player 1 earns strictly more than their min-max, we will directly construct a subgame perfect equilibrium to show that such a game belongs to the class CSPE. Because S prime is a Nash equilibrium by the Volk theorem, the payoff profile epsilon S prime is feasible and individually rational. And by using the Volk theorem again, there is a subgame perfect equilibrium S with the same payoff profile. Let us have a look at the path of play induced by the subgame perfect equilibrium S. Now let us modify S such that the path of play stays the same, except for the actions played by player 1 in stages that are a power of 2. Notice that if we modify the path of play only in stages that are a power of 2, or actually in any null set, the limit of means payoff does not change. Let us fix any actions C1 and D1 of player 1. In the stage 2 to the power of t, player 1 will play C1 if t belongs to A and D1 if t belongs to B. Otherwise, both players play according to S, but pretending that player 1 played according to S in test stages. What we mean exactly by pretending is that we define a map called fix that for a given history returns the same history with the actual actions of player 1 in test stages replaced by the actions returned by the original strategy S1 from the Volk Theorem. Now we can define the strategy of player 1 formally. It is a map that for a given history plays C1 or D1 if the next stage is a test stage, otherwise plays what S1 would play. Let us proceed with the strategy of player 2. In each stage, player 2 simulates one more step of Turing machines T1 up to T of logarithm of T. If any of them halts in stage TD, player 2 verifies whether player 1 played the correct action in the test stage, and if not, plays the minimax against player 2 up to the stage TD squared. So for the next TD squared minus TD stages. Why this construction works? In short, S bar is a subgame perfect equilibrium because S is a subgame perfect equilibrium by Volk theorem, and one can show that deviations in the test stages are unprofitable. The strategy of player 2, S2 bar, is computable. That comes from the fact that the sets A and B are recursively enumerable, and the strategies from the Volk theorem and also the map fix are computable. And last, no computable strategy of player 1 can respond optimally because A and B are recursively inseparable. The existence of a strategy profile S bar satisfying all these three conditions means that the game belongs to the class CSPE, and that concludes the proof. To sum it up, we derived the first complete characterization and showed that most of the games admit a computable strategy that has no computable best response, but either has a best response, forms a Nash equilibrium, or forms a subgame perfect equilibrium. It would be interesting to see if the similar techniques can be used and how the characterizations change if the payoff is computed as a discounted sum, or in a setting where players can randomize over the choice of the actions played in each stage. That's all from my side. Thanks for attention.